All right. I see you guys are really supportive of this. It's really early in the morning, right? It's 8 o'clock in some places and 6 o'clock in Turkey. I really appreciate you guys are joining us so early. All right. So we are live. This is just a picture from Turkey, not Turkey, from Tokyo. I was there a few years ago for an IEEE conference. So again, this is a collaboration with LUMS and STEMatters from USA. We are doing fundamentals of bio-nanotechnology. Let's get started. So quote for today, intelligence plus character. That's the goal of true education. We are not here just to become better professionally, but as in our character as well. So let's get going. We started a discussion in last lecture I shared. We'll be talking about a paper, basically a talk by Dr. Feinman, who was a Nobel laureate from Caltech. And this paper it was a talk to a conference, to a small workshop, and he called it There's Plenty of Room at the Bottom. I think it was 1959, and after about 60 years, we look back and we see that this was a real imaginative talk that laid out a nano vision. Things that we are doing today, things we take for granted today, they came from among many visionaries. This talk gave a concept of what we call atom by atom assembly, like placing each atom in a specific order. And many people believe that this is what can be called as the birth of nanotechnology or the vision of nanotechnology. He was so sure of his vision that he set some goals and he offered cash prizes for people who could solve his challenges. But there are many people who disagree with it as well because they say that he probably did not talk too much about the role of chemistry that it could play in nanotechnology, but he was more of an talking about biology and talking about engineering. Now, this is the paper that's given out to the registered students for homework. If you just search for the title, you would find the paper, and there are very specific questions that you have to address. One of those questions in your homework. So these are the two options. You can pick one and you can write your answer on that. So first topic is that how much of his vision has come true. So you will read the paper and then you'll have to do some further reading to see what are some of the things that have come true. And you have to give three examples. For example, you would see that he gave a challenge of uh, a moving part at micro scale, and in about a year or so, somebody won that prize. So you'll see that over years, many of those things have already happened. Or you can pick the second topic, which is where he talked about self-replication and molecular assemblers, which is still seems like a futuristic thing that can we make nanoscale bots that can make other nanoscale bots. So that's another uh, really visionary thing. And that's where you have to address that. Is it possible with nanotechnology? If it's possible, then where would this happen? Or if it is not possible, then what do you think are the major challenges to this impediment, to the nano assembly or molecular assembler concept? All right. So for registered LUM student, that's your first homework. And we can discuss, you can send me an email and we can talk more about uh, things as you explore. All right. All right. So let's get to the idea of what is nanotechnology and basically still looking at what has been driving uh, nanotechnology and what has been major driver of making us push down to make things smaller and smaller. This is a picture just to give an idea of scale, right? Size. how small is meter and then how small is millimeter, right? 10 raised to power minus 3 is millimeter. So that can be an implant. For example, the eye cornea is about 1 centimeter, and then something smaller than that would be 1 millimeter. And then if you divide further by uh, 1,000, we get into the area called micro scale, micrometers. And at micro scale, we have the what you call MEMS devices. Can somebody tell me what does MEMS stand for? Can type, can speak, anyway works for you. So MEMS is micro electromechanical systems. The idea is that micro scale things that can move. And we have MEMS devices all around us, right? From the gyroscope or accelerometer in your cell phones to any moving body or any moving part that senses somehow its position. We have accelerometers. Even we have MEMS parts in projectors. If you have seen a new modern projector, you see they have projectors which are like 2 inch by 2 inch by 2 inch. You can put them in the pocket, right? They have MEMS parts in it. There is a technology called DLP, digital light projection, that's used in modern projectors that has MEMS parts, moving parts in it, moving mirrors in that thing. So MEMS is very common. And then if you divide it further by 1,000, we get into nanoscale. So here's an example of carbon nanotube. And then again, some uh, biological things are shown on this slide. So now we ultimately are focusing on nanotechnology, but what has been driving us to make things smaller? What has been driving us to make things at smaller scale? So the number one driver has been transistors, or what you call electronic devices, right? So this is a picture of Bardeen, Bertain, and Shockley, who got Nobel Prize in '56 for their invention of transistor. So today we have billions of transistors on a chip of a centimeter by centimeter, but this was their original transistor, right? So it's a big, colorful picture of same thing. So what it is a three-terminal device. So we know resistor. Resistor has a constant value, but if you can transduce the resistance, if you can change resistance, if you make resistance go up or down, right? That's the concept of transistor. So they had this third terminal, which is making the device on or off, basic work of transistor. Now, that is from 47, and that's been pushed on and on to make many more devices. So I just said billions, but this is where it all started going small and slow. First, they made a planar transistor in 60, then they made integrated circuit, which means that they put transistors and capacitors and all the components, the discrete components that we know, right? Resistors, capacitors, inductors, they put all in one chip within the surface, and that's what you call as IC. And in same 1960, they made a prototype flip-flop circuit. And those who might have taken digital circuit, you know, flip-flop is uh, the most fundamental interaction in a digital circuit. And they put 4 transistors on one chip. That's the picture on the low right side. They kept on pushing to make things smaller and smaller. And Jack Kilby and Robert Noyce, they came up with the IC, concept of integrated circuit. So this picture on the right-hand side above is their first solid circuit oscillator, right? Basically 555 chip, what you call today, oscillator, right? You know 555 IC, electrical engineers in the room, 555, it's a timing IC. In any
Yes,
circuit,
sir.
we use 555, right? So what it does is oscillates, right? Oscillates at a certain frequency, and that drives your circuit. So that was the first uh, time that he showed. And the lower right side is the actual handwritten notes of Jack Kilby in his lab notebook. Now, Jack Kilby is, I think it's one of 3 or 4 Nobel laureates who did not have a PhD, but because he invented IC, and today we have IC. And now think about it, going from 1959 to that, we have come 20 years ago, we were making circuits, ASIC devices with multiple layers. With the left one is showing 5 layers of a chip, 5 layers of an IC. So think about it. Just from one, we have pushed so many things in down in about 40 years that we have billions of transistors now. So and this is still from more than 20 years ago, where on the left side is just a cross-sectional view. On the right side is this a chip where they have taken away the insulator, silicon dioxide, basically, what isolates devices from each other. So they removed it. So it is the actual interconnects and actual copper connections that go run in one integrated circuit. That black thing that we use, or microprocessor that you must have seen in your computers. So this is where we stood, and that's one of the technology drivers for nanotechnology. Now, there were other visionaries, other people. We maybe you have heard about Gordon Moore. So Moore's law is something we talk about. Moore's law in chip industry, in semiconductor industry, in nanotechnology, we all know about Moore's law, or what was the vision of Moore. So he wrote an article. It was not even a research article. It was just in electronics and journal Science magazine, where he said that in 10 years, there will be, and this was 65. So he was just talking about next 10 years, that he said that we would put 65,000 components on a single chip. So from that point where he was talking about, it was almost impossible. But then today we call it Moore's law, because what it meant was that every 18 months, the number of transistors or number of components on a chip would double. Think about it. It's an exponential growth. So this top right is a handwritten plot from Gordon Moore, which was showing that what was his vision, how we would go down and then we would shoot up in how many we can put on a chip. And then the lower one is, I know you cannot see it small, but I just want to give an idea that over years, from 1970 to up till now, we have been doubling number of transistors for the most part on a chip. We have started doing some other tricks now. We, instead of just doubling, we are now focused more on uh, operational benchmarks than number of transistors. We'll talk about that also later on. But for most of last century, we were pushing to put more transistors, more and more, to catch up. And so much so that by 5 years ago, we had 2.1 billion. And I have another slide somewhere. I'll share with you as we go on the actual recent one, which has 30 billion transistors on the chip. But that's the technology drivers. Those are the things which have pushed us to do more and more. Does anybody knows what kind of processor we use in Apple iPhones? These are called A series. So we have A6 and A8. So that's what's been pushing on Apple processors also. Now, when I say Apple, those are mobile devices. So mobile devices have different role. So they also have 2 billion transistors in them. In what, if you see the die size, that's 8.5 millimeter by 10.5 millimeter. That's 1 centimeter and less than 1 centimeter on the other side. And how many? 2 billion transistors. So think about it. Now, That's the technology driver. That's what we call that, how we have been pushing to make things smaller and smaller and to make things cheaper as well. So you can put in consumer devices. So A8, now when you look at the whole layout of a cell phone, then you can see that you have, uh, this is the whole processor, there is a whole chip or antenna and all circuitry that goes into an iPhone. And processor is just one small part of that. Right? Now here it says A8 is manufactured on a 20 nanometer process by TSMC. Now TSMC is Taiwan Semiconductor Manufacturing Corporation. That's not even in US. So in Taiwan, they're making processors at nanoscale. So this is what we call as real globalization in nanotechnology from people like Moore, from people like uh, Feinman. But what happened is in this push, we have been trying to make things smaller and we have been hitting the material fundamental quantum properties where we cannot, for example, we cannot use them for, we can use them as conductors, but we cannot use those material as insulators now anymore. So we have to look for other materials because we are becoming 2 or 3 atomic layer thick in those devices. So that's where we have kind of nanotechnology has transitioned in, and now we are going into where we say, okay, we want to make quantum computers. So that's all something we'll talk later on. Now, in computing, which has been the major kind of driver, we hit the silicon material uh, limitations long time ago in 2007. And then the industry changed and they say, okay, we can use other materials like silicon and gallium arsenide chips, or we can put totally other kind of materials like plastic semiconductors. But that again has different applications than uh, just processing, right? And so much so we have now on flexible substrates. There's a major area of flexible substrate, and that's where a lot of bio-nano work is going on, where we want to make like a band-aid or what you call saniplast to put a patch, and it has circuitry embedded in it, which can sense a lot of things. It can take sweat, it can do sugar level measurements, but that is still a push of technology to do computation in different forms, different approach, or different material. Right now, looking at this push and looking at reaching to the material limitations, there are new things that come up. And when I say new things, what I really mean is that the laws of bigger scale that we know, physical laws, chemical laws, electrical laws, they start breaking down. Because now when we talk about a few atom thick material or few atom interactions, they have very different kind of rules and regulations, different laws. So we have to come up with new theories and new kind of frameworks, new models. So that's pushed by many things. For example, material properties are different. We have melting temperature changes, right? So we know standard melting points for materials, but now when you make them nanoscale or you make nanoparticles of that same material, they would be melting at different temperature. The light properties become evident or become diminished. There may be conductivity, which things may become superconductive. So if we are using a semiconductor where we expect a band gap, where we expect some voltage gap, we'll talk about that later also. It may become superconductive, or a superconductor may become insulator. Chemical reactivities are way different. And that's part of the reason, because if for a bigger thing, if you take a big mass, say 1 kilogram or 1 pound, whichever applies to you, and we have a big block. But if you chop it down into, say, 8 pieces, the mass is still the same, but now you have more surface area. And that means, that's what the second bullet point means, that that greater amount of the material would now come in contact with whatever reaction we are doing, or whatever things we are exposing it to. So now that's another property which would be different when you keep on making things smaller and smaller. The mass may still be the same for the whole thing, but if you chop it down into very, 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 very fine pieces, then they would have different reactivity. Now, if we have this, then we face another dilemma. We reach quantum limitations, that we can start interfering with the band gap of a material. We can start interfering with energy of of subatomic particles, electrons and holes, if we make these materials too small. So, and that gives us an opportunity. What I say, nanomaterial properties can be tuned. So then we can adjust them to different applications, right? It can be, here I'm highlighting light fluorescence color, but it may be their conductivity. It may be we can put some other capping layers on top of that. We can make fibers out of them. So a whole bunch of properties that can be tuned. And then that more functionality gives us more opportunities to make newer products, right? So this is a little bit primer on what has been driving nanotechnology and what are the opportunities with that, right? So let's stop here. Let's see if you have any questions, because I want to get into nanoscale properties in a separate session. So let's see, questions.
Sir, a couple of questions. The first one is, you've mentioned how the number of transistors have been growing exponentially. So, I mean, what is the precise the laws governing that this process? I mean, I don't understand how is this happening. Well,
Right.
first we have.
Right. So this is a very, very fantastic question. Think about it. So if I have a 1 centimeter by 1 centimeter silicon material, right? And I have a crude technology, old technology, and I can make 10 by 10 array of transistors, right? So I would get 100 transistors in that area, right? Now, if somebody comes up with an advanced technology that says, hey, I can make smaller transistor on that same chip. And that person, I can put 100 by 100 there. So now 100 by 100 means I can put 10,000 transistors there, right?
Yes.
So that's what we are doing. And we will talk about semiconductor fabrication. And there you will see that how you could make VLSI design with billion transistors. But if you cannot translate them physically on a chip, yeah, design would be there in your computer, the VLSI file. But translating that is where the bottleneck of semiconductor fabrication comes in. And that's
And
we
is there and is there an upper limit to, I mean, how many transistors we can put on a chip?
so that's where the industry keeps on pushing. They are changing materials. They're going away from silicon. They are changing the technology or techniques, how they were making those things smaller. So and there are many drivers are coming in. So now, even instead of just one layer, there are multiple layers of those transistors that are interconnected between different layers. So it has become a 3D marvel of your microprocessor. So if you look at your microprocessor in your computer, it's not one layer. There are 8 to 10 layers of devices in there. So hence, we are not just using the X and Y real estate, we are also squeezing Z direction in that chip as well. And hence we say we are increasing the number of transistors in that. in that same area. Does it make sense?
Yes,
But this
it
is,
makes sense.
yeah,
Another question. Another question. You've mentioned about these properties of melting point and fluorescence. I mean, these properties only make sense for some lump of matter, let's say metal. But if we're talking about a couple of atoms, and I mean, there is no meaning to these properties, right?
right. So exactly, when we are talking about bulk, we talk about melting point, right? But when we are talking about a few atoms, chunk of few atoms, and that grain is so small, yeah, melting point, it would melt right away, right? Because there's no need for heat transfer. There's no need for uh, there's no resistance to flow of heat, right? So essentially, it would right away melt. So this is exactly why their properties are different. So, and the concept of melting itself goes away because you start heating and it's already molten.
I mean, the melting point itself is some temperature, right? And temperature is nothing but the intensity of oscillation of molecules.
Right. So
So I mean,
for the bigger material, we do have melting point for every big chunk. We have melting point for every material. But if you chop it down into small pieces, yeah, melting point concept of melting point breaks down there. And similar for electrical conductivity. Yeah, if you think about electrical engineering, you know, we have a wire and we put voltage and the current flows, right? Now we keep on making the wire thicker and thicker. We know the charge, most of the current flows on the close to the surface, right? So you make a thicker wire, you would have less current flowing. But if you chop that thicker wire into very small threads, and what we do actually when you get a cable, you see there are lots of finer threads in there, right? If you keep on making the thread smaller and smaller, you would have no resistance theoretically. So that's exactly what it means, that the properties of conductivity would change. And we'll do an exercise on the chemical reactivity also, which is the idea of surface to volume ratio.
What is the limit of number of atoms from where it becomes number of atoms to a surface or molecule maybe?
So you talk about limitation. Okay. So how small we chop it, there are now we don't when you talk about few atoms or grains, nanograins or nanoparticles, or if they are light emitting, we call them quantum dots. We don't chop from smaller pieces to we don't chop bigger pieces into smaller ones. Then we do what we call bottom up fabrication, bottom up synthesis. Then we do reaction, and we stop at whatever grain size we want. So we can stop at 2 nanometer, grains of 2 nanometer. We can get a solution of nanoparticles of size 2 nanometer. And we can calculate how many atoms would be there in 2 nanometer. But there has to be a, a basic kind of limit on few atoms come together and they have a physical mass to it, right? So for different materials or different applications, there would be different size that we would want. And for that size, we have very clear characterizations already available. Like what would be the wavelength we would get, what would be the intensity we would get for what concentration of solution. Yeah, so we have data sheets for all of those things. All right, yeah, boss,
I
go ahead.
Sir, I'm audible, sir.
Ahmed, whichever goes first. Go ahead, Ahmed, you go first.
Sir, my question is related more like if Moore said that twist are doubling the number of transistors, sir, in a chip, sir. If we follow that law, sir, so it's also increasing, sir, the number of transistors on a chip, sir. So it's also need a lot of power, sir. So how we can go with them?
And you are very right. The power management of these devices is another huge area in itself. Not just power consumption, but that power turns into heat. How do we remove that heat that the chip itself does not melt away? Yes, you're right. So we'll talk about that also later on. But this is a major problem. You guys know that you cannot keep your laptops in your labs anymore, right? They become too hot now, right? And that's a major engineering problem now, that we can keep on putting more and more devices, but can we sustain them to operate at that high temperature? And how fast can we remove? So there is a major push of finding materials that have high thermal coefficient. So that's also one area of semiconductor devices, that how do we do packaging that is better in thermal management and heat transfer. Yeah, that's also one issue. All right, Moaz, please go ahead.
Right, sir. So we heard about like I've been interested in gaming benchmarks and game processing performance of different brands. So we heard about AMD has 5 nanometer chips and Intel still is stuck on 7 nanometer chips. So are we talking about transistor sizes on those processors? That is the first question.
So what you're talking about is technology node. And all right, hold on. I have a slide on that. The next slide is about that. You talk about technology node. So when they say they are at 4 nanometer, or they're 6 or 8 nanometer, we are basically, so that's a figure of metric, which is the channel length. So it's that number is taken from channel length. And channel is, in transistor, we have source and drain, and then we have gate, and the distance between source and drain is what we call channel. And that length is what defines what technology node we are at. We'll talk about that in another lecture. So this was a slide which I had it here. I should have shown you. So the right-hand side from 2007 is 35 nanometer node, 45 nanometer node, where the gate length is 35 nanometers. So I think it's a square root of 2 that we take of the gate length, which is called as technology node. Now, when they say, okay, one company has reached that node and the other one is trying to, so the difference basically is that, yeah, we have standard technology, but then each company keeps on pushing to develop its own fabrication technology, which they don't share. And they may all have 4 nanometer, but one company may be working to make sure that the devices do not break down. There are issues of electromigration, there are issues of, it's called mean time to failure, MTTF. So in which they stress the chips to make sure they will not fail when they go to a customer, because customer is just going to return them. So that's what makes one company to start rolling out chips at one technology node, while other may take some time, right? But it has to do with the device dimensions and specifically the channel length.
Right. I have another question. So generally what we do is we run different benchmarks on these chips whenever a new chip comes out. So we run different gaming benchmarks on these chips.
So you are trying to test them and try to get to the failure, right? So to stress them out.
Right. Yeah. So
Yeah.
I wanted to know, because there are two different benchmarks of performance on which we base the performance of these two different chips. Like there is a single core performance and then there is a multi-core performance. And I would be interested in knowing the difference between the two and how we calculate that.
I think it would be that how efficient when you have multiple cores, then the multi-cores have to communicate with each other as well. So either you push the whole power in one core, or you divide it in 2 core, and you have to see that how is there change in difference in efficiency on distributing that. It goes into more on the testing of the devices than fabrication, because from the fabrication point of view, they would have been made in the same way, except they are on 2 different cores, and there are 2 parts of the chip which are fabricated together instead of putting everything in one chip, right? So that's probably the difference. But from the fabrication point of view or from the technology point of view, they would be the same. It's just the layout and the VLSI design of how you have placed those chips or the parts in those chips. All right, questions? All right, very good. Let's get the homework going, and I look forward to see you next Monday, right? All right, because for me, it's always one day behind. All right, I'll see you guys on Monday.
So when is the homework will be due on Monday?
Homework is due always next week, Sunday.
Okay.
Homework is always due more than a week, right? So today I've given it to you. You have until next Sunday to turn it in. So TA will be in touch with the registered students for that.
So can you kindly ask the TA to provide us some sample on which we can base our answers or something
It's
like
just
that?
a one-page write-up. It's just an essay you have to write.
Achha, all right. Okay. So
Just an essay.
we'll get in touch if I
Yeah,
have
be
any.
creative. Don't worry. There's no, okay, in this course, there is no hardcore benchmark for these things. Yes, so there are specific requirements. You have to look up for 3 examples or 2 examples. But apart from that, be creative. All right? All right. I'll let you guys go. I'll see you on Monday.
Assalamu alaikum, sir.
Alaikum.
Sir, I wanted to talk to you about the grading policy.
All right. So, yes, ma'am. I got your email.
Yes,
I
sir.
think I'll talk to LUMS professors and we'll take care of that. Don't worry.
Okay.
In this course, my concern is not your grade. So we have benchmarks. Let's keep on going through those. You'll be okay.
Thank you so much, sir.